So we continue our discussion for scalar fields in 3 plus 1 dimension, and in this lecture we will discuss two important aspects of scalar field propagators because that's something very special in 3 plus 1 dimension, so it's worth discussing it separately from 0 plus 1 dimension. Okay, so to begin the discussion, let's write the expression for the scalar field propagator again. So the momentum space propagator, the momentum space, I mean this is the also called also let me write the frequency space. For scalar field is minus I by h bar p square plus m square minus I epsilon, where p square is p mu. Okay. So now there are two important aspects we will discuss. So first important aspect is about negative energy solutions. So let's focus on relativistic on-shell relation. So okay, so first note that the pole of the propagator is controlled by the energy momentum relation. Right, it is given by p square plus m square. Since epsilon is very small, it's given by p square plus m square. So this implies that the energy, so in relativistic, this is true for all relativistic theories, that energy has two solutions. So both the signs are allowed. Then the question is that what is the meaning of the negative energy solution? We already have seen some aspect of it at the beginning of the lecture when we discussed the problem with unitarity. So now the question is then what is the meaning of the negative energy solution? Okay, so the meaning of the negative energy solution was actually given by Feynman, and we will see that how the Feynman I epsilon prescription the Feynman-Aliskal prescription captures it. Okay, so the Feynman interpretation is that positive, let me write positive frequency solution travel forward in time and negative frequency solution travel backward in time. Okay, and not only that, they travel backward in time, and then he said that this is same as antiparticle traveling forward in time. So how it happens? How these things happens? So in order to do that, let's try to evaluate the position space expression for the propagator, which is given by p square plus m square minus. Okay, so now this thing in the energy axis, so we will discuss the poles in the energy plane, and so let's draw the diagram. So E squared is E squared minus p vector squared minus m square plus I epsilon equal to 0. So E squared is equal to square root of p squared plus m squared minus I epsilon. Sorry, E is equal to this. Okay. So this means that you can show so that there is a pole. So in the complex energy plane, the pole is here and here. Okay, so this is p square plus m square. Now the important part is that so the energy part here, the energy part of this expression is simply exponential I p0 times t. Okay, so then depending on we close the contour upwards, sorry, this is actually this, or downwards, depending on whether t is greater than 0 or t is less than 0. So you can show that when t is greater than 0, we close the contour downwards. So basically for t less than 0, t less than 0, and we get contribution from this pole, the positive pole. Okay, so this basically justifies this interpretation that for positive frequency the solutions travel forward in time, because when t is greater than 0, sorry, this is t greater than 0, whereas when t is less than 0 we close it upwards. And get contribution from the negative pole. Okay, and again you see that this also basically justifies this point, that because that the negative frequency travel backward in time, because the propagator for backward in time, the backward part of the propagator only gets contribution from the negative frequency. And you see that both of these are happening is because of the clever choice of the epsilon prescription. So in this sense, epsilon prescription is extremely crucial to have this particular property, that we have only positive energy solution which propagate forward in time, and negative energy solution traveling backward in time. Because for retarded propagator, for example, for retarded propagator, both the poles contribute for t greater than 0. And then the problem is that what is the interpretation of the negative energy particle? Then the question is, what is the interpretation of the negative energy solution? What is the interpretation of negative energy solution? Because we do not see the negative energy solution in our real world, right? So then retarded propagator has this problem. But where you see that clever Feynman epsilon prescription solves this problem in a very beautiful way. It is said that the positive frequency solution travel forward in time and negative frequency solution travel backward in time. And then the whole point is that the negative, we'll see this interpretation with the antiparticle when we'll see charged particles, because in that case the meaning of the antiparticle becomes more prominent. And then these negative frequency particles traveling backward in time can be explained as some positive energy. So this is same as positive energy antiparticle. Traveling forward in time. Okay, so epsilon prescription does this job. But then there is also another important aspect we want to discuss, which is propagator and relativistic invariance and causality. Okay, so the main problem here is that, let's just review for us. So in Minkowski space, I have to be more specific. Let's say in 3+1 dimension Minkowski space, firstly the distance between 2 points. So let's say there are 2 points. x1 and x2. So this is x1 mu and x2 mu. Okay, so mu runs from 0 to 3. Okay, and the distance between 2 points is given by eta mu nu x1 minus x2 mu which is same as you can show that t1 minus t2 squared, the time difference squared plus the spatial minus the time difference squared plus the spatial distance between those 2 points. Okay. Now done. Sorry. Yes. So now the problem. Now let's try to understand. So two points are time-like separated if t1 comma 2 is less than 0. Okay, so this is the time-like separation, and you can show for two time-like separated point for two such for two time-like separated points, the sign of this quantity is relativistic invariant. What does it mean? It means that there is a meaning of the statement that which event occurred before the second one, before the other one. Okay, so I mean, if let's say t1 greater than t2, that means that t2 happened before t1. Okay, and as long as I mean, this is just simply saying that as if the sign of t1 minus t2 is greater than 0, then that also essentially means this. Okay, this is where saying, because t1 minus t2, this quantity itself is not relativistic invariant, but the sign of the quantity is relativistic invariant, which means that for such points there is an unambiguous notion of time ordering. We are going into this direction because we know that in order to define sometimes propagators, for example, for relativistic, for Feynman propagators, we need the notion of time ordering, and this is very important, that there is an unambiguous meaning of time ordering. Not just, actually not for that matter, not just Feynman propagator, but also retarded or advanced propagator also has a theta function, right? So the theta function, that's another way to say that theta of t1 minus t2 is relativistic invariant. For time-like separated points, okay. Whereas for 2 points are, if the 2 points are space-like separated, I mean, this proof is will be given in the lecture note. You can find there 2 points are space-like separated. Then sign of t1, t2 is not relativistic invariant. Which means that which event happened before the other event Is not, I mean, which event happened before the second event or something, it's not a relativistically invariant notion. I mean, if you go from one frame to another relativistic frame, you will find that the ordering of the event has changed. Okay, so in that means that for space like separated points, theta t1 minus t2 is not relativistic invariant. Okay. Okay. With this intuition, let's now discuss relativistic invariance of propagators. So first let's start our discussion with Whiteman propagator. Which is defined for this four-dimensional field theory. The Whiteman propagator is defined as this thing. Okay. Now here you can see that the point, the thing, everything in this side are Lorentz invariant. Why? The vacuum is Lorentz invariant. This is a scalar field which is Lorentz invariant. Then the whole thing is Lorentz invariant. Which means the Whiteman propagator is Lorentz invariant. Now what about retarded propagator? I mean, retarded propagator, when we defined it, so the retarded propagator okay, and this definition is true for any point, any 2 points. Now you see that even this object is relativistic invariant. The theta function is not relativistic invariant. Because for time like separated point, for space like separated point, there is no unambiguous meaning of the theta function. I mean, this can be justified by considering two space like separated point. Okay, which means that retarded propagator is not Lorentz invariant. Which means if you want to have Lorentz invariant quantum field theory, we cannot use retarded propagator, because then in that case the choice of the propagator will break the Lorentz invariance. The same thing is true for advanced propagator. The same thing is true for advanced propagator, because advanced propagator just has the opposite thing. Advanced propagator has minus T1 plus T2. The same argument holds. Now what about Feynman propagators? So Feynman propagator, has two pieces. So it is theta Ta minus Tb Ta Tb plus the other piece Tb minus Ta. No, now here is the most, this is a very interesting propagator, because here is firstly you see that for time-like separated point, separated points, you can see, you can explicitly see that the propagator is Lorentz invariant. Now for space-like separated points, depending on the choice of frame, so let me change the color here, depending on the choice of frame, either this one is non-zero, so let me call it term 1, or this one is non-zero. Okay, so then for space-like separated point, since any one of them is, it will depend on the choice of frame actually, but in depending on choice of frame, since one of them is non-zero, what we do is that then we say that this propagator will be Lorentz invariant if so for this we have to put for space-like separated point, if phi I, this should be xa xb xb xa. So for space-like separated point, if this is true, then the propagator is Lorentz invariant. Okay, and actually we can check Peskin and Schroeder where the computation is given. For space-like separated point, this is indeed true, and that's why Feynman propagator is Lorentz invariant. So this justifies our choice for Feynman propagator when we want to do relativistic quantum field theory, because in relativistic quantum field theory, Lorentz invariance is one of the important requirements, and we found that for relativistic theory this is required. The Feynman propagator is required because of coming from Lorentz invariance. Now another thing I want to mention, that this requirement is often called the causality constraint. Okay, so the causality constraint is simply saying that let me write that. Causality in relativistic theory. The causality constraint in relativistic theory says that two operators at space-like separated points should commute. Okay, so then relativistic, so in a causal quantum field theory, the hope of getting a relativistic invariant, the hope of having relativistic invariance is only there if we use Feynman propagators. And in that sense, Feynman, the justification for the Feynman propagator in quantum field theory basically comes from the relativistic invariance. Okay, so if you actually want to see this computation, I recommend you, for example, Peskin. This is given for space-like separation. Okay, and you should remember also this is a very important constraint in quantum field theory. So both of this actually explains the importance. So both of these points show us the importance of Feynman propagator and I epsilon prescription. Okay, so this concludes our discussion for the propagators in for a scalar field in higher dimension, in 3+1 dimension. The rest of the thing for the scalar field, when you try to do a computation with propagators and try to compute correlators, all of them are very similar to what you have already done in 0+1 dimension. So in that sense, we will not discuss it separately. But the important aspect in 3+1 dimension, or in actually also in 2+1 or in 1+1, the moment there is a space direction, is this causality constraint and relativistic invariance. And Feynman propagator manages to have those property, whereas relativistic retarded propagator or advanced propagator do not have that property. So this justifies for us the choice of Feynman propagator when we want to do relativistic quantum field theory in 3+1 dimension.